I'm Matthew Bertuzzi.
I'm Mohammed Iqbal.
I'm Mohammed Sarfraz.
And I'm Sanjayan Kalendran.
We are Group 14 of this year's Mechatronic Capstone class, and we are going to be presenting our design project, the Care Hockey Table. Throughout university, we all enjoyed the tabletop game of air hockey as an opportunity to spend time with friends while maintaining healthy rivalries. The game is able to help maintain a competitive nature because it involves critical reaction times, simple mechanics and rules, and high skill ceilings due to the fundamental skills required to play. As fans of air hockey, we saw an opportunity to improve the overall experience of the game through the implementation of higher quality features. Specifically, we had the desire to make the system autonomous and increase outreach through making the game more accessible, all while maintaining the traditional gameplay of standard air hockey. The need for the desire could be highlighted by the growth of the game of air hockey within the market according to Technavio. The additional autonomous nature of the game provided a good opportunity for challenging solo play, such as in the presence of a pandemic. With added accessibility features, the game would also be able to extend outreach to a larger audience incapable of playing through traditional means. Using the information compiled, the problem can then be defined as to design and implement a mechatronic system to modify or develop an air hockey table for providing accessibility options to people with physical disabilities, and adding an autonomous opponent without compromising its functionality as a regular air hockey table. Using this definition, research found similar problems tackled by Kei Ajita and A. Namiki, using high-speed cameras to predict required behavior of a robot-based opponent, while C. Mara et al. Developed an autonomous table. The latter highlighted issues with the implementation of a camera-based system, which included a high-glare surface, high-resolution camera requirements for accuracy, and the time cost of cameras. The implementations prevented the tables from being used traditionally and did not implement accessibility features. Overall, it was determined that the project objectives required the solution to be user-friendly, such that the users could easily switch between autonomous, accessible, and manual play, while the overall design should be safe and robust. Functioning to block any shot according to the level of difficulty, the table presents a feasible technical challenge designed for commercialized entertainment.
To best explain our final design, let's start off with a shot.
As the puck leaves the point of impact, it takes on a very linear trajectory. As it passes over the table, it activates corresponding Hall effect sensors on a series of sensor-slot PCBs. These sensors are pulled for their state every 1 millisecond, allowing us to read our puck position over 100 times on every shot. Each sensor half row is represented by a byte, and with 2 of these half rows in each PCB, a total of 2 bytes are sent by individual CAN bus chips through our data spine into our STM board, where all of the processing occurs.
The STM board is the heart of the system, with separate boards connected via CAN bus for managing accessibility and power. The STM board has been previously calibrated with knowledge of the position of each sensor. When the sensor triggers, the board knows the set of ranges of where a triggering puck could be at every pulling interval of 1 millisecond. Using a Kalman filter combined with linear regression, this history of sensor activations is used to generate a velocity vector for the puck in real time. With this, the system can predict where and when the puck will intercept our manipulator range of motion. It can even extrapolate shots that bounce off the wall.
This is all a modular design, as the board is only concerned with activations for a series of calibrated coordinates, and the slats are all connected via one bus. The table can have individual sensor slats fail, be rearranged, or ship with different quantities depending on the desired trade-off between accuracy and cost. In autonomous mode, the microcontroller would simply use the computed values to decide where to intercept the puck with the linear guide, and at what time the second degree of freedom should activate to send back a competitive hit. As we are in blended accessibility mode, we have a user that is using their accessibility input method of choice to set a desired velocity to the paddle. This is accomplished through our accessibility interface, supplying 3.3 volts over a standard 3.5mm jack to read analog values from a variety of adaptive equipment. Supporting many input permutations to help balance user fatigue, our user's input position is scaled to a velocity value.
These desired values are written to a trinamic stepper motor, turning the belt on our linear guide, moving our carriage in the desired direction. Mounted on the carriage is our second degree of freedom, a capacitor-powered solenoid that moves a magnetic stack with a punching motion for offense. The paddle above, with magnetic inserts, follows the movement of this magnetic stack, and therefore the carriage. A plate mounted below the linear guide, itself below table surface, completely seals moving components, aiding user safety. Left unassisted, however, the use of a novel input method and the precise positioning requirements of the air hockey table would mean that most gameplay would result in misses. Our blended assist takes our computed intercept value and creates a conic well potential around it for possible manipulator velocity. This makes our final paddle position from player input to be very likely around the point of interception.
In other words, our player is much more likely to make a successful response. Of course, the game can always be played as a regular table with a lack of instructions using a quick swap of the paddle. With the table turned on, a simple Bluetooth start command can be sent to calibrate the linear guide and put the table in a functional state. Starting in autonomous mode, shots traveling over the outlined white rectangle on the table are tracked using the Kalman filter and linear regression algorithm and pinpointed with the linear guide to defensively return shots with a magnetically controlled paddle. If the user desires to play with a friend requiring accessibility control features, a simple mode switch command can be sent to change the table to accessibility control mode. Using foot pedals as the accessibility control device, as shown in the video in the bottom right, a player can manipulate the paddle in a unique manner with the aid of aim assist. Without the punch mechanism for the second degree of freedom, the prototype still demonstrates potential for offensive play through sideswiping. Finally, with another simple Bluetooth command to switch modes, the table can quickly be adjusted to manual mode. With a quick swap of the puck and paddle, the table functions as a typical table. For the use of the mechanisms employed in the final design, the table does not require any overhead changes to maintain the aesthetic of a traditional table, with added functionality. Overall experience with the table highlights its ability to provide multiple options for entertainment. As an added demonstration, we included a video of autonomous gameplay to show the haste with which the system responds. To further explain the iterations and validation of the final design through the prototype, we'll start off with the sensors and algorithms developed. Central to the overall system is the ability to track the trajectory of the puck as it travels over a two-dimensional array of sensors. With a 12-sensor array configuration depicted on the right, a variety of sensors including Hall effect and capacitive were tested to determine characteristics of the sensors for detecting through a distance mimicking the thickness of the air box of the table. Testing indicated that the SI7203 discrete Hall effect sensor from Silicon Labs provided sufficient sensitivity for detection, negligible hysteresis, sufficient pull rate, as well as an omnipolar package to negate puck orientation. With the discrete Hall effect sensors selected, the system started as a single board using an isometric grid pattern to maximize data along the X and Y axes. However, due to cost and mounting complications, a modular approach was opted for. First taking the form of 8 sensors per slat connected to a single CAN bus spine with the MCP25020s, the design was modified to double the amount of sensors per slat to form a linear spine by rotating the boards, each communicating 2 bytes of positional information. To validate the modular sensor slat system, prototype boards were created using an offset isometric grid pattern with 16 sensors. However, the CAN GPIO extender selected was replaced with a 16-channel I2C extender due to the ease of use and lack of one-time programming. Using a total of 80 sensors, 5 boards were mounted adjacently to create an isometric grid pattern with row and column spacing of 3 centimeters. Through incorporating LEDs into the design, post-fabrication analysis could be completed to verify sensor response to a magnetic field. With the lights off, the stability of the sensors through a lack of flickering indicated robust sensor design required for the application. Through communication with the STM-based microcontroller used, the system struggled to adequately pull data at 1 kHz using a 100 kHz I2C baud rate. Incrementally increasing the baud rate to 500 kHz indicated no issues with communication nor noise, validating the requirement of a higher bit rate that a differentially signaled CAN bus could provide.
Determining the trajectory of a magnetic puck as it travels over an array of sensors was aided through the use of MATLAB, where simulations were designed to model a point passing over an array of discrete sensors. The simulation permitted the modeling of sensor characteristics, such as pull rate and hysteresis. Due to the linearity, time invariance, and symmetry of the system, the statistical method of linear regression was used to efficiently determine the trajectory of the puck along the path of triggered sensors in real time. However, the method lacked intuitive collision handling and required many sensors, driving up costs. As a successor, a custom-derived Kalman filter was developed from a dynamic model for intuitive real-time trajectory tracking. The first figure on the right depicts the filter operating with low process uncertainty, struggling to correct for collisions. With greater uncertainty, the adjacent system responded well, but was noisy in estimates. To improve performance, the dynamic model was adjusted through modeling wall collisions, producing much smoother output as shown in the last figure. To reduce the overall cost of the system and potential points of failure, a hybrid system between the common filter and linear regression was developed. We were able to automate and analyze each possible system configuration's response to an exhaustive batch of shots of various origin and angle. With custom visualization tools, we were easily able to compare the system performance of different quantities of sensor slats and see how important manufacturing tolerance in sensor placement was for each. Here we can see the effects of diminishing returns in increasing sensor board counts above our chosen 20, but appreciate how lessening the count makes each system more sensitive to manufacturing tolerance. To further validate the algorithm and sensor slat board design, 80 sensors were used in the previously discussed configuration. Due to the need to retrofit the board design, a compacted array was used to allow greater shot variety, while enabling validation of software-based simulations. Additional methods of calibration were used to validate array positioning beneath the table in addition to manufacturing tolerances. As shown on the right, a small magnet could be used to pinpoint the position of the sensors, while geometrical methods could be used to define a skew angle to locate the grid orientation. For accuracy validation, we pinpointed 3 positions on the table relative to the coordinate system defined in the top left of the screen, and fixed the positions with small magnets beneath the table for repeatability. The location of the sensor grid is indicated by the outlined white rectangle. Taking shots at a variety of angles, the trajectory of the puck relative to each position was determined using a high-speed 480 fps camera. Using the data obtained, the true and predicted intercept of the puck were compared to determine the relative positional error. Using a kernel density estimate of the straight and wall shots, the data follows a promising normal distribution, with a bootstrapped 95% confidence interval of approximately 10 mm error for the mean of the shots modeled with perfect accuracy. The results indicated formidable performance of the system, with shots only missing outside of the 75 mm interval. The prototype sensor distribution was modeled in MATLAB using the same batch program as used for the final sensor script. Sampling the results of the model, at the 3 origin points of our test shots, 98.6% of the predicted intercepts resulted in real-life success as well, and qualitatively, error trends in the model against shot angle reflected what was seen in reality. All of this provides confidence that our model is representative of real performance. For timing validation, the goal was to ensure that the strike mechanism would accurately strike the puck. Shots were taken using the same high-speed camera to calculate the collision error. With a Bluetooth signal to simulate the delay in actuation of the striking mechanism, the number of frames between the collision and strike, as indicated by a collision message on the Bluetooth terminal as shown, were counted. The data indicated a converging trend of increased collision timing accuracy as shot speeds increased. Comparing the straight shots to wall shots also indicated that at higher speeds, more characteristic to air hockey, the wall and straight shot errors converged for consistent timing. The results above help understand that a strike mechanism having a full stroke time of approximately 200 milliseconds will be sufficient to ensure proper collision timing.
To best represent the overall electrical system configuration through the prototype and validate the final design schematics, we used an STM32F4 breakout board from Mice Ionics to represent the main processing core of the system. Soldered in through the I2C pins of the processor, jumpers were connected to form a bus to the sensor slat boards. Through a separate UART channel, an Arduino was used to validate the accessibility control board connected to the control device through a serial header. Added to the board was a Bluetooth module to enable remote control and communication for mobile application validation. Finally, through a CAN transceiver, the trinamic stepper motors were connected to validate CAN bus configurations at a 1 meg baud rate. Using a DC power supply, the power requirements of the system were validated at small scale through monitoring wattage of the constituent parts. It was found that the motor had a nominal current draw of 1 amp at 24 volts due to the limited loading, while the remaining system drew a total of 0.5 amps at 3.3 volts. The figure on the right depicts the draw of the sensor slat board array. The configuration used validated accessibility control at a low 57.6K baud, while the overall system performance was stable and reliable. To validate the final software design, focus was targeted towards developing the FreeRTOS task-based system, where priority was on development of tasks related to sensor monitoring, algorithm performance, and motor communication. Using real-time trace monitoring of the main control board, it was discovered that the partially completed system boasted 98% idle time, with sensor slat bus communication dominating the load. The FPU of the processor also proved beneficial for precise algorithmic calculations.
We now cover some of the mechanical aspects of the project. For the 2 degree of freedom manipulator, a linear rail guide from HEPCO Motion was selected for the base degree of freedom. Based on calculations that were cross-validated with the manufacturer's literature, the forces and moments exerted during use were well within the factor of safety for the carriage, bearings, and rail. With the inclusion of the 2nd degree of freedom and enclosure, the linear rail guide was paired with a 4:1 gear ratio set to ensure the selected motor met the calculated torque specifications. A DC solenoid was selected for the 2nd degree of freedom given its compact housing and weight, and non-linear analyses were performed on the solenoid and magnet enclosure to ensure potential von Mises stresses would not cause part failure. To provide optimal magnetic force interaction between the paddle and manipulator, part of the inner frame had to be removed. To ensure frame rigidity and minimal deflection, the width of the outer frame was extended by 3¼ inch. The entire frame thickened by an additional 1/4 inch. FEA simulations were performed on the table frame, where scenarios range from manipulator assembly weight at rest to the lateral force exerted at maximum acceleration. Non-linear studies with symmetry boundary conditions were used with metrics such as deflection and first principle stresses, considering the brittle behavior of wood under extreme loads. With a modulus of rupture of 80 megapascals for MDF and 48 megapascals for a 10-year use span, the FEA scenarios reported no first principle stress larger than 25 megapascals and minimal deflections. Like the final design, the prototype table was modified to allow the manipulator to span the entire width. While lateral movement and vertical deflections were acceptable for testing, the upgrades made to the final design were visually justified and would be beneficial to the prototype. With the incorporation of the magnet with the puck, design goals were based on minimizing the change in dynamics of the puck collision. Factors to minimize were change in mass, center of gravity, and dampening effects of the magnetic connection. With the magnet mounted to the top side of the puck, it resulted in a center of gravity shift that torqued the puck when it collided with objects, as seen in the video. The use of soft-cured adhesives also resulted in damped collisions and reduced speeds. By inserting the magnet inside the puck and using more rigid adhesives, the embedded magnetic puck had similar collision dynamics as the original puck. These factors validated the design choice to have an internally embedded magnet in the final design, with hollowed sections to minimize mass increase, and snapped design to minimize manufacturing time. The magnetic interaction between the paddle and puck was also a key component to be validated. The interaction between the puck and paddle was tested through taking consistent shots along the table side and measuring the difference between pre-collision speed and post-collision speed with a 480 fps camera and standard square inch grid pattern on the table. Approximate velocity estimates could be obtained. The data was analyzed for the relationship between pre-collision speed and post-collision speed as a percentage of pre-collision. Although the post-collision speed of the normal puck was agnostic to initial puck speeds, when the speed of the shots increased to 1.5 meters per second squared, the magnetic puck's post-collision speeds began to converge with that of the normal puck. As a result, at higher speeds, the higher kinetic energy of the puck dwarfed the loss of energy resulting from magnetic interactions over an inelastic collision, rendering the magnetic puck effective at typical air hockey speeds.
For accessibility control, as discussed previously, the accessibility interface was replicated through the use of an Arduino to process analog inputs for controlling the paddle. Provided that control devices operated within similar voltage ranges, they could easily be swapped to provide endless accessibility control options, including that of the foot pedals used for the prototype. To improve the overall system control at high speeds and reduce the learning curve, aim assist was implemented using a design similar to a conic well potential, applying forces to help guide the player to the target position with the sensor algorithm. To validate the design, we first see that as a shot approaches and the user depresses the left foot pedal, with the aim assist mechanism activated, once the target position is reached, the well force prevents the user from moving away until the shot has completed. On the next shot, it is demonstrated that without touching the controls, the paddle does not move. In the final shot, when the user attempts to move away from the target position, a large force is experienced which counteracts the desired movement until the shot is complete.
To conclude, there are still a few areas we would like to have seen the prototype be a more accurate representation of our final product, including the use of the final number of sensor boards, mounting the manipulator within the main assembly, and testing other accessibility control options such as face tracking. Additionally, the implementation of a 2nd degree of freedom punch mechanism would have verified our offensive performance. However, this aspect of the project was not prototyped due to the retrofitting table damage that it implied, as well as mass limits of the linear guides we used. In addition to the challenges mentioned, manufacturing constraints prevented the development of a lightweight adapter for our linear guide carriage to securely hold our magnetic actuation assembly. With the uncertainties in shipping time and availability of a replacement table, it was decided to best manage the risk through building a prototype that validated our concepts without potentially causing replaceable damage to the table. To the completion of this project, we developed our skills in self-organization, as under our COVID-influenced circumstance, we learned how to do this using planning tools and conferencing services such as Microsoft Teams. With the restrictions in our physical prototyping ability, we poured more time into ensuring that we modeled our systems as thoroughly as possible in tools such as MATLAB to ensure our first prototype iteration would have no surprises. Thank you for watching, and we hope to hear your feedback soon.